Hi, everyone, and welcome to Pathfinder, a podcast by Payload, the leading digital media company in the space industry. I'm your host, Mo Islam, and we're joined today by Stefan Powell, CEO and CTO of Dawn Aerospace, a New Zealand-based space transportation company that develops satellite propulsion systems and space planes designed for rapid reusability. Stefan and I break down the business, discuss the development and records of their Aurora space plane, and much, much more. Tune in. Stefan, great to have you on the show. Thanks for being with us.
Yeah, thanks a lot, Mo. Great to be here.
So tell us a little bit about Dawn Aerospace. What are you guys doing? What are you guys building?
Yeah, so Dawn Aerospace, we see ourselves as a space transportation company. You know, it's about going from Earth to space and from space to everywhere else. When we sort of started this problem, looking at this problem in around 2015, 16, we thought, like, maybe we should get a company together around, we had been working in the space industry. There was kind of this, like, awkward tension in the industry of, like, we could all see that there was this awesome future coming where there was going to be thousands of satellites around. There was about 3,000 at the time. Everyone could see that this hockey stick was coming. Everyone was working on smaller electronics and making satellites much more capable, moving to distributed systems. But there was this real awkwardness of, like, we haven't really got the technology to actually do that, though. Like, things aren't scalable. Transportation is not a scalable thing yet. That became a really problem, but like a clear problem for Dawn to be working on, like scalable, sustainable space transportation. So that's what Dawn Aerospace is all about.
So paint us a little bit of a picture of, it's 2015, you said 2015. There were a number of launch providers out there, a number of different companies working on similar problems. Maybe tell us a little bit about, like, what inspired the founding? How did the team come together? What was your thought process on the market landscape at the time that propelled you to want to solve this?
Yeah, so like partly what I just said, like, but then really the extension of that is, like, yes, there was this awkwardness, and it was a clear problem that we needed to solve. It was clear that, like, there was some really obvious opportunities in space, right? Like communications and Earth observation and all these ones that we know. Like, it's pretty clear, and you can see now that, like, Starlink is a huge thing. There's going to be multiple Starlinks in every like geopolitical realm. They're going to need to have their own Starlink, and then there's going to be a version of that for direct to cell as well, and there's going to be Earth observation versions of these as well. Like, everyone's going to need probably about 5 or 6 different constellation types, and then duplicated in every relevant geopolitical domain. Like, USA is going to have their own set of constellations, and Europe and China most certainly as well, and Russia's working on the same thing. So, like, there's going to be not tens of thousands of satellites, but hundreds of thousands of satellites at some point. I don't know exactly when, and I don't know exactly what the applications are going to be, but it's really clear that they're all going to have to get to space, and they're all going to have to move around a whole lot when they get there. And the more agile, the faster they can do this, the better. And so this was relatively obvious, even, I think, 5 or 10 years ago. What's not obvious exactly is the timing or the application, but I don't think that really matters as long as you're working with this massive tailwind. It was clear, though, that this is only going to happen if the price of launch is going to go down really significantly, which means the cost penalty of things like electric propulsion or like an efficient system go way, way down. You don't actually need to be that light anymore. What you really want is to be very performant and very agile. So chemical propulsion seemed like the really obvious application. And in whatever you were doing, you needed to be able to do it at extreme scale. Like, by extreme scale, I actually probably mean about 1/10 or 100th of the scale of the automotive industry. So it's not actually that extreme. It's just extreme for space, because everyone's used to doing, like, onesies, twosies of stuff. And so, we're not talking about 100, we're talking about 10,000 or maybe 100,000, which is extreme. So, like, this, I guess, even as students in 2013, 14, and then as professionals in 15, 16, this was a pretty obvious. Like, it seems like there's no way that this couldn't happen somewhere between now and 2050, right? It's just got to happen in our lifetimes. So, like, this is a very obvious problem for us to work on. And the real problem was, like, there's just no solution for how you do any of this scalably. It seemed like SpaceX certainly have a path, and I think SpaceX has astounded everyone in just how scalable they've made the current architecture. and like they're making fantastic progress with Starship now. So maybe I think that's a solution that could scale pretty well through the 2030s. But then if you want to go even beyond that, I think when you're talking about thousands of launches a year, servicing hundreds of thousands of satellites, um, I still have my doubts about the general architecture of a rocket that is so impactful on the other users. Like it's really hard to fly a space like a Starship when there's other aircraft flying around. So how are you going to do thousands of these a year? While there is actually a model, like an airline model, they're also very high performance things. They're also 50% filled with propellant. It wouldn't be any different if it was 90%. But flying them with an architecture that is just much more aircraft-like, there's literally as many flights of aircraft, commercial aircraft, within about 2 hours as there has been space flights ever. So this is a clearly much more scalable architecture in general. And then the same with in-space propulsion was like we need to just have a way more scalable, robust, probably refuelable way to actually make this reality, like this future that we're envisioning, possible. So it was this tension that was just like, guys, we've got to start working on this problem.
Well, you're alluding to it a little bit, but maybe tell us about your core products. So what are you building? I know you keep alluding to the plane itself, but maybe tell us a little bit about the product.
Yeah. So um, the end vision is really clear. I think the hardest thing about aerospace is trying to come up with a set of products that lets you go there, right? Because I'm not going to be able to go raise like definitely more than $1 billion to go and solve any one of these problems all at once and get to that 2050 future. That's just ridiculous. And also, you're just so far ahead of the market. Even if you perfectly predict it, you don't want to go do that. So yeah, the first product that we came up with was essentially hydrazine replacement. That's the like catchphrase selling point, right? But it's nitrous oxide and propylene. Very common, easy to use propellants. We thought we were going really out on a limb with these propellants because they'd never been used in space before. We were essentially students that had a lot of experience with them. And it was pretty easy to see how you could use this in a satellite and it would be really effective, pretty high ISP, up to sort of somewhere between 280 and 300 seconds of ISP. Super compact, super easy to use, super easy to customize for new users because the tanks are just plain tanks. They don't have propellant management devices. They don't have that many valves. And then it's all super simple, essentially like barbecue type gases. Open the valves, fire a spark plug, and away it goes. Glorified cigarette lighter, easy. Now, of course, you need to make this work properly in a satellite context and be hyper reliable and radiation tolerant and blah blah blah. But this seemed just so much easier than hydrazine. And essentially these Silicon Valley people who realized that data was the new gold, they wanted to build satellites. They weren't going to use hydrazine. They were using electric propulsion because that was the only thing that's really available. But actually, they just want to move faster. They value time much more than they value a low launch price. So they really wanted chemical propulsion. But this was the inroad, right? It's just a way more accessible product, but that's still scalable across the entire satellite range. So yeah, that was kind of the first really obvious product.
Before we jump to anything else, I do have a question. How much did the sort of the sustainability angle play into some of the design decisions there?
Sustainability in terms of the environment,
Yeah.
like not, we're not doing it to save the trees so much. I don't think satellite designers, they don't make decisions based on that, right? But it's sustainable in the sense that you can actually do this at scale. That's kind of the key thing. Like if you think about trying to launch 100 satellites at one time, and they're all filled with hydrazine, and there's something like a 1 in 1,000 risk that a hydrazine system is leaking, and you're going to have to completely take that stack apart, and it's going to be a human life danger on the ground to launch this thing. Now, 10% of your stacks are going to have this issue where you have to take them apart. Is that really sustainable? Like, can you really envision a future where we're launching hundreds of thousands of satellites that are hydrazine fueled? Not really. Not unless you can get this reliability rate way, way better. And that's just by virtue of having such a dangerous, nasty stuff. That's fine if you're launching 1 or 2 or 10 satellites like that. That's totally sustainable at that low scale, but sustainable at high scale? No, no way. Like, you need something that's way more robust, way less consequential when things go wrong. Because, like, when you start doing a lot of anything, statistically, you're going to have things go wrong. It's just like, there's no way around that. So sustainability is way more about being able to deploy at scale without completely breaking the system.
Right. Right. So was the propulsion was the desire to go into propulsion technology from day one part of the okay, well, we're going to do this first because we know there's near-term revenue here, and that will help our larger vision?
Also because it's one of the things, and it's the largest single, most costly single subsystem in a satellite, and it's the
Hmm.
thing that every satellite's going to need. Like
Right.
like every satellite's also going to need reaction wheels and magnetorquers and whatnot, but those are much smaller, simpler things generally. Propulsion was the single largest, most complex bit of a satellite that every satellite's also going to need. So
So
that's the common denominator.
I actually I want us to pause here for a second, and Stefan, I want to actually talk about you. Like, how did you get into this business? Like, how did you decide to start this company, and who did you bring along for the ride in the early days?
So I started studying at TU Delft in the Netherlands, which I think I really lucked into. It was one of the few high quality universities in Europe that had a course starting in English. I could speak German reasonably well, but I knew I didn't want to study in German. Um, so yeah, anyway, I ended up at TU Delft. Also being a Dutch citizen really helped. And then I later found out that it was like a top 20 aerospace university in the world. So great, lucky me. Um, I I also went there because it had a very prominent footing in aerodynamics and in like sustainable engineering, like particularly around wind turbines. I was very interested in that at that time, like energy systems in general. But then I got to university and I realized there wasn't very much practical that you could do. Like, I'd spent my whole childhood building things in the shed with my dad, building everything from huge catapults, trebuchets to go karts and whatever. I was just a very practical person, practical family. Um, but yeah, once I got to university, I realized that there wasn't much I could actually do with wind turbines. It's all just theoretical, unless you really enjoy Navier-Stokes equations, which I didn't very much. The much more practical thing to do was actually hands-on engineering at the local rocket club, which was Delft Aerospace Rocket Engineering, and that was an environment that was supported by the university, but you set your own goals. So we formed a team. We set our own technology goals of developing some new engines with a vision to be able to beat a European record, altitude record. So our club already had that record at the time, but we wanted to double or triple it or whatever. Um,
What
and
was the
I
what was the record at the time?
think the record was like 12 point something kilometers, and we wanted to hit. We wanted to like double that at least. So yeah, they were using pretty simple solid rocket motor technologies at the time, like we call them sugar motors. Um, but yeah, so we wanted to develop higher performance engines. So we started building hybrid rockets, which was a relatively simple step up, nitrous hybrids. We spent about 5 years doing that and went from our biggest engines being a few hundred kilograms in thrust. The biggest engine we built was about 1.3 ton of thrust. And we were like undergrad students at this point building that. Finally graduated in 2015, and that year, with a team of about 50 people, I think we'd spent about 200,000 euro on the project by then. Raised all that money ourselves, our own sponsors and whatnot. Organized this whole trip to Spain to this, and I don't know how we convinced this military base to let us launch this rocket from there, but we did. Had the Spanish Armada out over the Mediterranean, clearing a whole space, and it flew, Mach 2.5 up to, um, about 21 kilometers altitude, which was super awesome, and I got to push the button on that. Like, I was the head pyrotechnician, had the keys around my neck to actually fire the thing, which is just an awesome experience. But this whole experience also taught me that, like, man, this is so much effort for like 2 minutes of glory, of 2 minutes of this thing flying, and then it was in the ocean. Like, how much time and effort would it take for us to redo that? And the answer was like, well, almost exactly the same. Like, there really wasn't, like, the marginal cost of this flight was huge. And actually, interestingly, like, the flight that we most recently did with Dawn effectively replicated this performance of getting to the same altitudes. But, we could literally set the aircraft up again and fly again 6 hours later and redo it. So, like, the marginal cost had gone from 200 grand of capital cost plus 2 years of 50 people's labor for free. And now we had reduced it to like 10 grand.
So that experience was the impetus for founding Dawn.
Absolutely. Yep. Just the realization we could do this so much better.
Was anyone on that team you were on part of Dawn today?
Yeah. Like half a dozen of them at least, including 4 of the founders. Yep.
Okay, great. So now tell me more about this, about what you're developing.
Yeah. So what we're developing with Aurora, it's really about. So once again, it was kind of like planting a flag far in the distance of saying the ultimate way to get to space would be more aircraft-like than rocket-like. So, if you could do it with, like, even take the reaction engines concept of a single stage to orbit aircraft, that's obviously the dream. That's super far out, super hard. I believe there's a bunch of stepping stones. The one that we've publicly talked about is a 2-stage to orbit vehicle where the first stage is an aircraft. So the near-term thing to prove is basically that you can have the same performance as a Falcon 9 first stage, but in something that's truly an aircraft. So takes off from a runway, certifies an aircraft, comes back, put more fuel in it, fly it again hours later type aircraft, not space shuttle aircraft, not even Virgin Galactic aircraft that's, weeks to turn around. Proper 737 aircraft. That's the goal. And the deeper we get into this, the more we realize there's actually even more stepping stones that are super interesting. So we start with an aircraft, right? Because we want those properties in the end product, but we also want it through the entire development cycle. We want to be able to go out and test rapidly and reusably, because that just lets us move faster. So we obviously start from the side of the performance spectrum where we're very low performance, but we're extremely operable. Rapid reusability is baked in from day one. And now every time we go out and fly, we fly higher and we fly faster. So that lets us also push things along certification-wise and technology-wise in terms of the ground infrastructure that we need. These are the 3 key elements, I would say, where the regulation and the ground infrastructure is actually probably more important and more driving when you really get to it. So now we're at a point now where the aircraft is the highest performance vehicle in the world in terms of climb rate. And in the not too distant future will be the highest performance aircraft in terms of altitude that we can reach. And then after that, it'll be Mach number that we can reach. And that will, Aurora, the whole point of that is to show that you can do this first stage performance, albeit at a subscale with no payload, but you can truly fly a first stage trajectory with an aircraft. But this is not that shit crazy or anything. This is totally doable. And actually, with relatively small amounts of money, you can show that that's feasible. And then it's just a case of scaling up to whatever you want.
Can you tell us a little bit about the flight from a few weeks ago?
Yeah, it was a lot of fun. We've been building up to this for quite a while. The previous years had been all about proving that the vehicle worked, and now the last 6 months has just been pushing the performance, like every time, just really ramping it up. And so every flight felt like quite a jump over the previous one. But we had done several flights up to about Mach 0.9, and that's when things start to get spicy. Like, we start to hit the transonic regime. That's where your aerodynamic models, like, you can simulate what's going to happen there, but there's so many non-linear effects going on that it's genuinely reasonably hard to predict exactly what you're going to see. And we knew that we were going to see some instabilities in the aerodynamics. So we had anticipated that, but it was just really interesting actually punching through it and seeing exactly how the vehicle responded. But yeah, like it was a very smooth flight in the end. Thankfully, being a rocket, you can crank through that regime pretty quickly, so you don't spend too much time in it. But absolutely perfect day for it. Perfect weather. Low winds at altitude. Iago, our pilot, flew flawlessly as well. And yeah, it was pretty simple in the end.
So you went Mach 1.1.
Yep. Yeah, that's correct.
For the non-engineer here, and for maybe the non-engineer listeners, tell me a little. So I know you've been doing flights at 0.9, and you're alluding to it a little bit. Like there's non-linearity, and there's a number of things that you can't test. It seems like I am kind of curious more about that threshold. How important is that threshold of going past Mach 1, and why is it that you can't test it in a facility on the ground?
Yeah, like a wind tunnel. Like for sure.
Yeah, like a wind tunnel.
Like you can test it in a wind tunnel at a subscale, but then some specifics about the aerodynamics are different. Like your Reynolds number, I'd call it, is not the same anymore. Like airflows are different at small scale than they are at large scale. Now there are some similarities, so for sure you can say something about it, but you can't say for sure how it's. You can definitely reduce the risk with wind tunnel testing. But part of our methodology also just means like we can just go test it for real, and it's not that expensive or that hard. Like why would we sink hundreds of thousands of dollars into wind tunnel testing when it's actually not that expensive to just build it and try it? That's part of the point of our methodology. But yeah, like flying for real just means that we're always dealing with the highest fidelity data. We can make real decisions. At based on actual flight data. So the significance of getting through Mach 1 is really, really high. Like that is the most uncertain bit of aerodynamics, right until you get to about Mach 2 to 3, where thermal starts to become an interesting problem. Like Mach 4 and Mach 5, where thermal starts to get really hard. Like things are actually getting proper hot by then. So yeah, we have a reasonably straight shot now through to about Mach 2.5, where aerodynamically things are actually much simpler in the supersonic domain than in the subsonic domain, because everything is it's just much more predictable mathematics behind what's going on. You have shock waves and stuff, but that's all actually quite simple to predict what's going to happen. And yeah, I guess it's actually easiest to look back at history and look at the development of aircraft, like how long aircraft spent at about the Mach 0.8, 0.9 realm, and they really couldn't get supersonic until there were some really big significant changes where they figured out, shit, this is how we go supersonic. And once they cracked that, the time from that supersonic flight through to X-15 going like Mach 6.7 wasn't actually very long. This was like less than 15 years to cross that boundary. And that's really representative of actually just how easy things are once you're supersonic. But that transonic regime is really the crux of it.
So this flight was Mach 2. Mark 2 of the Aurora.
Yeah. So
okay.
This is the second rocket-powered aircraft we've built.
Yeah. So tell us a little bit about the roadmap to transition from where you are right now to fully orbital capabilities, and what are some of the major kind of milestones, technical and inflection points that you need to hit to get there?
So like I kind of alluded to, I think Starship is actually going to solve the orbital problem probably through the 2030s. I think that's actually going to be enough, and there's probably not a huge market there for a rapidly reusable spaceplane. So the next market that we actually jump to is hypersonic aircraft. So there's a whole lot of applications in there, primarily in research and development right now. Funnily enough, the US government alone is spending about $7 billion on hypersonic research, not deployment of anything hypersonic, but just research into materials, sensors, engines, defense technology generally in that area, which is actually a significant fraction of the entire launch market now, is like literally just one user looking into hypersonic research. So as the highest performance aircraft ever built, we have a very unique position to change the way that this testing is done. Right now, across that $7 billion of expenditure, US government gets less than 5 minutes of test time at relevant hypersonic speeds. They're even looking to like re-entry capsules as ways to test hypersonics, because there's just so little access to this regime. Like BARDA just signed some, $45 million contracts for hypersonic testing on re-entry capsules. So like rockets don't struggle to get to hypersonic speeds. They struggle to do it in a cost-effective way. So if we can put rocket performance into an aircraft architecture that is truly aircraft-like, rapidly reusable, low marginal cost of use, then absolutely we can get hours or days of test time at hypersonic speeds with a rocket-powered vehicle. And that's kind of the key tool that humanity needs to actually learn about the hypersonic regime, and progress these domains. So that's the obvious next step. That doesn't require a huge amount of expenditure. There's not a lot of competition in this area. There's not a lot of good solutions. We can modify our technology to go there, and that'll give us an extremely solid platform of knowledge and capability from which we can then look to two-stage to orbit vehicles, and eventually fully reusable as well.
So right now, and correct me if I'm wrong, but right now it sounds like because of Starship capabilities, you're saying, hey, well, look, it doesn't make a ton of sense for us to focus on that market right now. So what makes sense right now, near term, is focusing on hypersonics. And as we mature and build that technology out, we can then revisit the idea of a two-stage to orbit and then figure out rapid reusability. That's what it sounds. That's what I'm hearing.
Absolutely. Yep. Like going to space with an aircraft is like the ultimate thing that you would do with the highest performance aircraft you could ever imagine, but there is a ton of interesting markets along the way, provided you are truly aircraft like.
So, specific to the focus on hypersonics now, tell us a little bit about how that has affected your perspectives on customer base. Now, obviously, the government is a big. You're alluding to this. There's the government's paying companies like Varda because there's not enough options for them to focus on that are more direct to what they're looking to do. So maybe tell us a little bit about there's the government customer, but what does the commercial landscape look like?
Yeah, so there is a large commercial landscape there as well. Like there's a lot that you can do with a vehicle, which is truly an aircraft, um, especially because you're able to go higher than balloons go, which is 30 kilometers, but lower than satellites go, which is about 250 kilometers. There's whole parts of this atmosphere termed the ignorosphere because scientists know so little about it. But these regions of the atmosphere drive a lot of climate science, like long-term climate science, as well as near-term, like weather prediction. So there's a whole massive market. Microgravity experimentation, I mean, like that's the primary reason that people go do research on the International Space Station. You can do at least a subset of this research or like precursor studies using suborbital microgravity at a tiny fraction of the cost. So we're talking with partners in the US who already sell into this commercial sphere. Pharmaceuticals, in space manufacturing companies that are all looking at this. There's lots of different opportunities there. But the most obvious immediate one is essentially satellite technology development. So people who want to test how a piece of satellite tech is going to work in a relevant environment for a few minutes, maybe. It's pointing an infrared sensor through the entire spectrum of the atmosphere and looking at Earth. You don't need to go all the way to orbit to that. You just need to go really high. So that's very obvious stuff to do. But like ultimately, we're discovering tons of new markets because this is a whole new capability. Like this is a blue ocean, technology really. So we have about 4 customers signed up already to fly on our current aircraft, which is not even going close to the full performance mission of flying to space, 100 kilometers altitude twice in a day. This vehicle can go to about 25, maybe 30 kilometers altitude if we're really pushing it. But that's already very interesting for them. So we'll be flying those commercial payloads sort of in around March this coming year. We've got a lot of other commercial interest. Nothing I can talk about specifically yet, but there's certainly people who see the immediate commercial potential of this vehicle.
And how are the conversations with government customers going?
Yeah, good. Like once again, they can see the potential of how this can change what they're doing, and it's coming from areas that we didn't necessarily expect. Once again, it's in those domains that I've just mentioned. It's government customers who want to understand the ionosphere better because how it affects their satellite communications is this is a super niche thing, right? That I didn't expect. They currently spend a surprising amount on suborbital capabilities, but they can only use those once every 3 to 5 years. Having a capability where they could, do these missions multiple times a week or even a day, where they could deploy something in the ionosphere. They used to do remote sensing of how that thermite is burning in the upper atmosphere, and now they could do direct sensing of it by deploying it on one flight and coming back and flying through it, completely changing how they're thinking about their research. This is happening in so many niche domains. It takes quite a bit to tease out, and especially government customers are not super fast to react and change, but they're certainly seeing the light.
How do you think about the opportunity in hypersonic weapons?
So the opportunity there, especially for us, I don't think is great on we're not a great hypersonic weapon. We're rapidly reusable. Uh, Kill vehicles are not reusable. So this is not our strong suit, right? Nor is it where we want to go. Like I don't think that's our role in this whole thing. What we can do is push forward our general understanding of hypersonics, which for sure has weapons application, and that's fine. I would say it's very similar to the jet engine development through the 30s, 40s, and 50s, where absolutely the first applications of this were military, and that's probably going to be where the early money comes from. Um, but the bigger applications, once you get to the 50s, 60s, 70s of the jet engine, is actually in the civil domain. And I think our role in hypersonics is more akin to we're trying to develop the core technology, the understanding of how this actually works, and the key tools that you need to understand that domain, rather than providing the end use application of it.
What's the what will be the payload cargo capacity of sort of the the initial commercial version of the product?
Relatively small,
Yeah.
because the fundamental science that they need to do is usually on small test samples or holding something out in the free stream, or even holding some avionics captive on board. So we're talking like 50 pounds. So these are not large vehicles. This is not multi-ton things that need to fly around. You can do a lot of very useful science and in a very efficient manner with a relatively small vehicle. So the whole vehicle size is like less than 2 tons. Probably actually more in the range of about 1.2 is what we're penciling in for our next generation vehicle.
What is how large do you want to scale this long term? Like, I mean, is the goal eventually to have a much larger platform?
So at this stage, we make sure that all the technologies that we work on are scalable. Like that, there's no reason you couldn't build a 200-ton takeoff weight version of this, which would have a 50-ton second stage on board and get multiple tons into orbit. That's entirely feasible. Like A380s are 500-ton plus vehicles, so there's no reason why you couldn't do this with an aircraft type architecture. Exactly how big we want to go and when, I think needs to be a customer-driven story. Now that's part of the challenge of working in such a blue ocean type market, right? Like if you think about the Venn diagrams of the markets that we're looking at, you've kind of got orbital launch, which is like, depends on who you ask, but let's call it 11 billion US is numbers I've heard frequently quoted. And then you've got aircraft, including like passenger and freight transport, and everything is about 1.3 trillion. So it's like massive in comparison. I'm not saying we want to do passenger transport or freight transport yet. Like those are further off concepts. But you take a small subset of that 1.3 trillion. Definitely, the hypersonics market is almost entirely in there. That's 7 billion US just in the States. Europe's doing a bunch there too. The existing aircraft portion of that, let's call it about 10 billion. And then you've got this whole space in between these two markets, which is, it's not an aircraft because we're higher performance than aircraft, but it's not really a rocket yet. It's somewhere in between. How big is this market? This is suborbital microgravity. This is pseudo satellite remote sensing. This is the blue ocean, right? How big is that? I'm not really sure, and I'm not really exactly sure what type of vehicle is needed to serve that market. But that's what we're finding out. We hypothesize it's north of 50 billion for this entire market. Now you'd need a fleet of different types of vehicles to do that. But there's pretty significant opportunities in there for vehicles that are even like less than 2 ton. Like think about like a pseudo satellite type capability. I want something that's going to get 3 minutes of visibility on a target, which is basically what a LEO satellite gets. But I want it to have really significant standoff from the thing that I want to observe. So not like a UAV, because they have to get pretty damn close. Like even a Global Hawk is within like SAM-site range. But a rocket-powered aircraft that can fly to 100 kilometers altitude can get there in 3 minutes, completely on demand, get eyes on target, like a satellite, but it's not predictable. So, there's, how big is that market for this tactically very useful pseudo-satellite capability? Probably a fraction of the existing satellite market, but that's still pretty significant.
No, that's super, super interesting. So I want to take a step back. I have a question. I think you're very well suited to answer what I'm about to ask, which is, so we're in this era. We're looking at hypersonic test beds, platforms, weaponry. In some cases, transport of people, supersonic and hypersonic. And it's amazing to see the number of great companies and startups that are kind of building here. But I have a question. We had the Concorde, we had supersonic. Now, obviously, at the DoD level, we've had amazing technology. But I even just at the commercial, I'm just purely on the commercial, not even thinking military. We had this interesting, great technology. The Concorde obviously was one of the one of the more commercial examples out there that ultimately didn't work, and the business model did not work. But I'm kind of curious, and actually, and to that point, there's also now companies like Arion and Boom Supersonic that are trying to build this. Boom recently lost its engine manufacturer, Rolls-Royce, and it created a lot of major issues for the company. I'm just curious, like, what has been so difficult and hard about taking this technology and making it commercial? And I know it's different from what you're trying to do. I mean, you did a great job explaining sort of the market as a whole and then sort of where you guys fit into it. But I'm just more specifically kind of wondering, like, what has been so difficult and complex? And also, like, the development, even when you look at a lot of the companies out there who are building larger scale hypersonic platforms, like, it is, many, 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 many years. And oftentimes the propulsion itself takes like a decade. Like, so talk to me a little bit about that.
I think you're so close to nailing it yourself. I don't think you even need me to answer it. I think a lot of them are trying to go for a market that I'm personally very skeptical of, which is like supersonic or hypersonic transport. Frankly, I think the jury's still out about whether there is that much marginal benefit in shrinking like New York to London time by a half, when so much of your time is spent at the airports at the end anyway. Like, surely the easiest thing is actually just to figure out how to get through TSA in 30 seconds, not half an hour. Like, that's the easiest time to win, right?
Yeah, yeah.
If I really want to go faster, that's the key key element there. So I think that conflating that problem with the actual just trying to understand hypersonics in a more fundamental way, that's actually where most of the money is going now, not into hypersonic transport or payload delivery or something. And for that, you don't need a fancy engine. Like I said, rockets go way beyond hypersonic. They get to Mach 27. Like that's an orbital system. Rocket Lab can use the first stage, and in some cases the second stage for haste. Like that's okay, repurposing of an orbital booster for a hypersonic capability. Wouldn't it be great if we just had an aircraft that could do that? Like I don't need to bend physics or have some different engine or some scramjet or Venus is building which honestly I think is super cool. Like I really want this stuff to work. Their RDE plus like rocket-based combined cycle engine is super fascinating, and I really want it to work. I just don't think it's a prerequisite for solving this problem. So you can skip the 10-year engine development and just jump straight to the basically it's a regulatory problem and a ground infrastructure problem. And I really see this as the SpaceX model. Like Falcon 9 was not a fancy engine or a fancy rocket, and vertical landing was done in the Apollo era and then again with DCX. None of this stuff was new. The only thing that was new was that they figured out how to put it all together and get it to a scalable, usable fashion. That's how they get a 10x outcome. That's how they bring the launch cost from $200 million a launch down to who knows how low it is now, but probably sub 20. That's the 10x outcome I want. We can do the same just by using existing aircraft, existing regulation, existing ground support systems, existing engines, put it all together, and you'll get something that's easily 10x better than a current system.
So no, I think that's a great explanation. You mentioned, you talk about scaling. What are the most significant hurdles for you when you talk about scaling ops and manufacturing?
Like by far the hardest things are the things that you can't throw money at to solve. Like engineering problems, you can solve with time, with money, and great people. Regulation is really hard, and I think SpaceX are once again a great example of that. All the might and money of Elon Musk and the FAA is still the long pole for them. And frankly, they're not doing anything particularly exotic. Like from a regulatory point of view, they're just launching a 2-stage rocket.
Yeah.
You want to fly a hypersonic vehicle as an aircraft? They don't really exist. Even supersonic flight over central USA is basically just outlawed. Like you just can't do it. FAA won't let you. So where are you going to do this? How are you going to do this? That's the thing that we've paid the most attention to, and I think is our real secret to why we're so effective. We already have a license that allows us to fly at unlimited speed with our vehicles. Now, of course, unfortunately, our vehicles can't quite do unlimited speed, but we're not, regulation is no longer our long pole because we operate in an area, like geographically, in New Zealand. We have an extremely progressive, future-oriented regulatory system for aircraft certification. And we have geography. We have the benefit of the South Pacific, which is the least used air and sea space in the world. So we 45 minutes south of our headquarters here in Christchurch, we can fly our vehicle out over the ocean, literally at unlimited speed. There is no restriction on this. US programs have to go to usually Guam or Australia to do this sort of testing. Or they have to fly as an orbital system, in which case, they fly on haste and fly out of Wallops, which is like it works, but it's not aircraft-like. It's not going to get you towards, this future where you really need aircraft-like rapid reusability. So that's by far the hardest challenge that I think we've already solved.
What's it, you're alluding to some of this, but what's it been like building in New Zealand?
Oh, great. Like fantastic. There's absolutely a reason that that Rocket Lab's done well. when you're trying to do really new stuff, sometimes having people who aren't maybe burdened is a too strong a word, but they don't have a pre knowledge about what the solution is supposed to be, you get a lot more out of the box thinking. You get a lot more like genuine creativity. I think New Zealanders are genuinely really fantastic at doing this. There's like Rocket Lab has just been a great case study for this. But generally, it's just a great place to live and work. It's not hard to attract high quality foreigners to New Zealand as well.
What is the space ecosystem in New Zealand like?
Yeah, small but growing is what I would say, and genuinely very talented. Um, yeah, I think that probably
Yeah.
sums it up.
No, that's no. We had a conversation with Peter Beck a few weeks, or actually about a month ago. But yeah, we talked a little bit about New Zealand, and obviously, it's great to see that there's two great companies. We want to see many more, and I'm sure I'm missing some. I'm sure I'm missing some.
So I would say Dawn is about half Dutch as well. So we've always had a very significant presence in the Netherlands, and that's especially key for our satellite division. Building satellite propulsion. Um, we as a space company don't want to reinvent every single wheel. Some things you do just want to do the established and proper way, and then having really deep established knowledge is super useful. So being able to draw on both, which I think Rocket Lab does really well as well, is like that's how you get the best of both worlds.
I want to go back to the business for a little bit. Talk to me about the revenue mix today. You have a propulsion business that's quite successful. You're in R&D mode on the plane, but obviously going quite well. You've broken a number of records. Things are things are progressing nicely. So clearly, I would assume a lot more of the revenue is coming from propulsion than it is today. But tell us a little about what it kind of looks like today, and then where do you see that growing?
Yeah, so our revenue is like more than 90% from satellite propulsion. Um, we're pretty close to being profitable. Like we're basically breaking even as a company now. So our satellite propulsion division is just about able to support the entire company, which is great. That's about 75 people total. The space plane, the Aurora program is about 30 people. We've raised about 20 million US to date, and we've done more than that in revenue now. So that's really a nice thing, and another major differentiator between us and other early stage aerospace companies is that while I believe we have a vision for this big future in 2050 plus, we've figured out what these early steps are that we can take that actually solve real needs. Like there are real customers for our problems now. Um, so yeah, that's
So you've opened up a totally new set of questions I got to ask you now on capital efficiency. So I actually to go back to your New Zealand based brother Peter. I asked him a very similar question, which is like, and I understand, setting aside size differences, obviously what you're building versus what the launch providers are building. There's a scale difference for now, but that being said, there's a lot of companies out there that have spent a lot of money and have shown very little real technical, commercial progress. I admire Rocket Lab for a number of reasons, primarily because they've been pretty good. They've been pretty efficient with capital, and even in the development of Neutron, they're pretty on track with what they've always said, what it's going to cost. And they've been very good about that. And I've asked both Peter and Adam the same question: how do you stay capital efficient? And Adam has joked that they anything above like $20,000. I forget exactly what he said, but everything above that, I'm looking at it. I'm making sure. Like, are we? But so tell us a little bit about how you've thought about capital efficiency. I mean, $20 million is not in the industry that we're in, not a lot of money, especially given sort of the progress that you've made so far.
Yeah, like honestly, it's the same thing. Like this is not it's not something unique to Dawn. I think it's just unique to space companies that are doing well, and it's relatively easy to say, um, these markets appear to actually be flooded. Like there's a lot of launcher companies, there's a lot of propulsion companies, but there's not a lot that are doing well, both in terms of their product and in terms of just the general health and efficiency of the company. And these things, they're only things you can hide from for so long. So like it's very clear when like which ones are floating to the top, and they're absolutely the ones where the leaders care about the details. So like this like Adam Spicer's quote about like he everything I think it was $30,000 needs a business case. Like we're at a smaller scale, so for us it's more like about every $5,000 is every like we're looking at that. But just generally, just having like caring so much about execution, about every little decision, it can feel like micromanaging sometimes, but it really is just very important that the leaders in the company are on top of exactly what we're doing, and we're only doing the most important stuff. And honestly, being quite ruthless about that is very important. So it often feels like tough decisions, like you go down a path and you start doing something and it looks good and you keep doing it. And then you get to a junction where you're just like, God, we can't keep doing this. This is just costing too much money. It's actually way harder than we thought. It's actually dumb. We just have to cut off this limb. And like you see SpaceX do that all the time as well, right? Like the early versions of BFR were massive carbon rockets and they were spending God knows how much money on this, but they just completely changed tack. Like that takes real guts to do that. Rocket Lab has done the same, with killing reusability on Electron. Neutron has had some major permutations already. Like an ability to be self-reflective and change as needed is incredibly important.
Yeah, no, well said. What do you think about the launch market these days with Starship coming? There's Starship and then there's everyone else. What do you think is going to happen to everyone else?
I mean, I wish I knew. I think there's two main ways, two main lenses you can look at. Like there's the commercial lens, which is just they're just going to whip the pants off everyone if they hit the price targets that Elon's talking about. Which okay, take it with a grain of salt for sure. But man, scary numbers if you're building a launcher right now. And then the other lens is this is still a strategic capability. You absolutely can't be fully reliant on one producer. That's just not going to be acceptable for so many people. So there will need to be others. It might be a little bit artificial that they are being supported, but like ultimately, I don't believe what SpaceX is doing is unreplicatable, or that I wouldn't even necessarily agree that it's optimal. Now, I'm probably not the best. I wouldn't be in the strongest position to critique that, but Rocket Lab absolutely could come up with a better way to do reusability. I don't think that's a crazy notion.
Sure.
There's many answers to this, so absolutely other people could be competitive with them. It's just that they're pretty significantly behind at this point. The same is true for any number of competitors there. But ultimately, I think that still the biggest single differentiator is execution. It's not technical decisions. So it's really just about their ability to just kick ass with the money that they have. That's going to be the differentiator between the successes and the failures.
What does success look like for Dawn over the next 10 years, or in the next 10 years, I should say?
On the in-space propulsion side, that's really just scaling up the solutions that we have. We're getting quite a lot of interest in our something we haven't talked about at all is in-space refueling. But we have our solution for in-space refueling, like the customer side docking port, is going onto several systems this year. Should be launched in 25, maybe early 26. Looking at how we actually affect in-space refueling is that's the next big leap. So absolutely, in the next 10 years that we want to have this as a solved problem. But otherwise, scaling that technology to really be able to deliver to larger constellations. We're already delivering to several Earth observation and communication constellations, but having that roll out to the extent that integrators look at the market and they say, we can go to automotive style, um, development where, a Bosch produces the oxygen sensors for basically every engine built in the world. They don't need to develop their own in-house technology like SpaceX had to do with Starlink, because it was just frankly like there was no one who could conceivably produce the number of reaction wheels and the number of propulsion systems that they need. So that's like the in-space side, getting to a mature supply chain, where Dawn is a major supplier of propulsion, and then onto in-space refueling. And on the rocket-powered aircraft, the spaceplane side, it's really about just continually pushing the envelope of what you can do with aircraft. It's pushing that out and finding the real markets for this. Where the immediate one is strategic space access for suborbital capabilities, atmospheric research, satellite technology, um, yeah, and then on to hypersonics as the next frontier of, the strategic space access gets you to about Mach 3.5. The next generation vehicle will be about Mach 5.5. But once again, just finding the killer application there, like exactly how fast, how much payload, how performant does it need to be, and nailing that, and then using that as the next platform to find what that next market is. Which beyond that, I don't know exactly, but that always becomes clear once you're two steps away from it.
So you've been at this since 2015. Tell me one thing that you've learned about being a CEO, founder, CTO, that you feel like, looking back on it, you're like, hey, if I could tell 2015 Stefan this one thing, things might, maybe we'd be at this point, or we've accelerated here, or just a learning that you'd want to share.
Yeah, maybe two things. Like execution is the common denominator. It's almost the only thing that matters. Um, Technology decisions or poor other decisions can always be, like, almost everything is a two-way door and you can go back on it. The real important thing is how well you execute on those decisions. It's by far the leading, yeah, um, KPI, if you like, of a good company versus a bad company. Uh, and the other one is, that we use internally is like people, process, product, and in that order. Like you have to get these things right. Even if you think you have the right product, if the process to make the product suck, it's going to be a crappy product. At least when you get to scale, like you might have made the first prototype work, but if the processes suck, it's not going to work at scale. And if you have the wrong people doing these things, then it's all just going to break. So you really have to be constantly revisiting, have I got the right people? Have I got the right processes? And then have I got the right product in that order? It's yeah, the realization of that being the key to a healthy organization, and then a good outcome from that organization that's been a learning curve for me.
Yeah, no, that's those are great thoughts. I do want to put a number three for you that I want to set up for you, which is before we started recording, we were talking about questions and well, high level, I should say, and we were talking about I typically like to ask people if there's anything that's like really off the table. Um, and you said nothing. You're like everything's on the table. You said
Yeah,
if we can't share, if we tell me a little bit about that, because I thought that was an interesting point. I don't hear that very often, if I'm being honest, and I want you to share that.
yeah, okay. The only reason I didn't include this when you just asked me is because I think this is something I've believed in for the longest time, and it kind of relates to the first point. Is that I think being worried about competition is just stupid. Like it just doesn't make any sense. Um, I feel like you should be able to tell people your plan and still beat them. Like you came up with the plan, you're going to be best placed to iterate on that plan and actually execute on it. And hence execution is the most important thing anyway. So yeah, I should be able to go to my closest competitor, tell them all my plans, and still beat them. And frankly, if I can't, then they were better at executing and they deserved to win. So like there's just no need to keep secrets about the core business, at least in those domains. Of course, there are some secrets that we have to keep. There's ITAR and EAR, and there's our customers have their own information that we're not going to divulge. So I'm not saying we'll tell everyone everything all the time, but especially what is core to Dawn should absolutely be public.
I love it. All right, well, one day I'm going to travel to Christchurch and you're going to show me around and everything's going to be on the table except the ITAR, except for the regulatory things, but we won't get you in trouble. But no, Stefan, this is great. Really appreciate you having you on the show. Appreciate your thoughts, your the story. So thanks so much. This is great. And at one point we'll do the show live from New Zealand.
Yeah, absolutely. Come by for a flight.
Awesome. Thanks, Stefan. Till next time.
Thanks, man. Have a good one. Bye.